No, no. Now there are T-beams on the steel exam. All right, let's get started. I saw this article on the news, and I thought I would share it. I don't know if anybody saw this. This was out of Chattanooga. This was on Monday. Fortunately, nobody was injured, but a little bit of a sobering, reality about what it is we do in this class. This stuff kind of matters a little bit. Fortunately, and seriously, nobody was injured. It looks like what happened was an oversized truck just drove over it, just too heavy, so girder failed. But yeah, nobody was injured. That's what matters. Okay, so if you notice, I actually have a lot of stuff written on the board. That's nothing on the board that you see here is anything new except for what's over there, but we're going to talk about that today. So everything below that line you can kind of just ignore right now. We'll talk about that today. This is our how we handle long-term deflections. Everything we've been doing up until now has been instantaneous deflections or immediate deflections. In other words, you put the load on the bridge, what's the deflection? Or put the load on the beam, what's the deflection once it's been loaded immediately? Now you do have a homework on this, homework 7. It was assigned Monday. I actually didn't have it on the announcement slide last time because my announcement slide was kind of full. But fortunately, it's only 2 problems. It's a somewhat short assignment. And after today, I'll sort of show you a way that you can organize these calcs, and it makes the homework go a little faster because we're going to do everything sort of tabular. But yeah, so today what we're going to do is we're going to continue on this example with deflection. And this example 15, there's a part A and a part B, and it all kind of goes together well. Like you'll see how it all fits together here in the end. But let's just sort of get back into the world of deflections, and let's make sure that we're all clear in terms of where we're at and where we're headed. Now again, the big thing to remember, this is a service limit state, so we're not accounting for load factors. We're not accounting for 1.2 dead and 1.6 live, because if we violate a deflection limit, it does not necessarily mean what happened in Chattanooga would happen. It just means that the beam's going to deflect too much, and you might get some cracking or excessive deflection or something like that. So now again, you all can calculate deflections using virtual work or what I taught you in 312. We're, for the most part in here, going to deal with pretty basic loading cases, so the formulas are pretty easy lookups. And as you know, the complicated part, or what makes, what's the concrete design component of this? I mean, you all have been able to calculate deflections, since last semester, so what's new? What's new is the moment of inertia. Remember, if you have a beam and you apply some loading to that beam, typically what's going to happen is that some of the beam is going to be cracked and some of it isn't. So what value do you use for deflections? You use an effective moment of inertia. You don't use your gross moment of inertia or your cracked moment of inertia. You use something in between. And that in-between moment of inertia is really a function of your applied moment. The more moment that you put on the beam, the more deflection that you're going to get. And so the way that we reflect that is the more moment, the lower your effective moment of inertia. So your effective moment of inertia is right here, and that's this formula. I put this on the board just so I don't have to keep referring to it back and forth and back and forth. It's a function of 4 quantities. 3 of them remain constant throughout your problem, and that's the gross moment of inertia, the cracked moment of inertia, and your cracking moment. So whenever you're computing effective moments of inertia, these 3 quantities stay the same. Okay. What changes is your applied moment. So as your applied moment changes, you're going to get a different moment of inertia. And that's why you cannot compute a live load deflection directly, because the beam never experiences just the live load. It experiences the dead load, and then it experiences the dead load plus the live load. So if you want that component of live load deflection, you have to compute the dead load deflection, and then you have to compute the deflection due to the dead load plus the live load, and then take the difference between the two. So let's say this causes 0.245 inches, and then the dead plus the live causes whatever, 0.7, well then the live load deflection is the difference between the two. And the reason why live load deflection is an important quantity to compute is because a lot of the deflection limits that we use, a lot of the ways that we determine whether or not a beam is behaving sufficiently is dependent on that immediate live load deflection. So just keep in mind that you cannot compute that directly. You have to take the dead plus the live and then the dead and take the difference between the two. And we talked about that last time, how more moment equals more cracking. So you can't really quantify how much cracking comes from just the live load. All you can do is do both and take the difference. Okay, so we started this problem last time, and I'm going to show you sort of a different way of organizing your notes for the deflection computation. And I think you're going to find that this makes the calculation pretty straightforward. But let's just sort of recap where we left off. So we're computing the instantaneous live load deflection for the following beam. So here's the beam, and let's sort of recap where we left off last time. We had computed some fundamental parameters. We had gotten the cracking moment, we had gotten the gross moment of inertia, and the cracked moment of inertia. Remember, this is the beam in its fully intact state, and this is the beam in its fully cracked state. So any of the effective moments of inertia that we compute has to be between these two values. So it's a check to see whether or not your math has been done correctly. Now we have E. We're going to need E for our deflection computation, so I went ahead and wrote that up here. And we have our dead load deflection that we computed last time. So let me sort of transpose this onto the notebook, and I'll show you sort of a different way that we can organize this. And basically it's just one big table. So here's my notebook here, and I'm not going to write down the parameters all over again because they're in our notes from last time, and they're pretty easy to find. So I'm not going to do that. And I'm just going to call this my example 15 notebook because we're going to come back to this here in a little bit. So let's look at our deflections. Okay, so let me draw a big table here. Okay. All right. And this might seem, I'm actually going to move this down a bit because I want some room up top to put some labels. Okay. Okay, so I want y'all to help me out with this. So let's look at our cases. The first case that we computed was the deflection due to the dead load. Okay? And I want you to help me with a couple things. First off, what was our applied load under this case? How much load was on the beam? 1 kip per foot, right? So that's the nice thing about deflections. We really don't care whether or not we're dealing with dead loads and live loads, because with deflections we just treat them as loads. So this is 1 kip per foot. Now, what was our applied moment under this case? Does anybody remember? Say it again. 50 foot kips. Now, remind me, how did we compute that? Like, what did we do to get MA? We had WA L squared over 8. Does everybody remember that? Now, I want to ask you all, what's the danger moving forward with other types of problems with just saying MA is WL squared over 8? Elaborate. Like, what do you mean by shape? Well, simply, what else? Exactly. If it's, this only works if it's a simply supported beam subjected to a uniformly distributed load. So if you have point loads on the beam, then it's not WL squared over 8. For point loads, it would be PL over 4. What if you have distributed loads and a point load on there? So you have to combine the two. If you don't know what formula to use, don't use a formula. Break out CE312 structural analysis, right? Draw the shear diagram and draw the moment diagram. I know you know how to do it, and just take your maximum applied moment. So everybody sort of see where I'm coming from? So again, I'm going to go ahead and label the column in this fashion because everything's a uniformly distributed load, but just be careful, okay? Don't just blanketly go, well, Dr. Mike said that's the formula, so that's the one that we use. No, be careful with that, okay? Sound good? All right, I just want to make sure everybody's clear on that. Now, what did we do next once we had an MA? What did we compute? IE, okay, so we had an IE, and that was, that was in inches to the fourth, right? Now, what value did we get for the dead load case? 4713.5 inches to the fourth. Now, does that value make sense? It's in between those two quantities, right? Make sense? All right. And then the last thing that we got was a deflection. Now, so first off, let me put just a formula here, and this is MCR over MA to the third IG plus, the rest of that. Now, I'd argue that this formula may change depending upon your loading configuration. This one won't. This is always the way that you compute the effective moment of inertia because it's just a function of whatever moments you get. Okay? Now, real quick, how did we compute this? What was our formula? Let me ask you this. Is that always going to be the formula that we use here? Are we always going to use that formula to compute deflections? What if you have a point load? I mean, I'm asking, you tell me. I mean, what do you think? Is everybody with me with what I'm talking about? I mean, let's go, here, let me show you something. So, let's just make sure everybody's clear on that. So, once this computer decides to load. Remember this? Remember our design aid, design formulas? And remember, 5WL to the fourth over 384 EI, that formula only worked if that was your load, right? If you had a simply supported beam and a uniformly distributed load. My question is this. What if I change the loading? What if I change it to a simply supported beam with a point load in the middle? That's not the right formula. The formula changes, okay? And if you don't know what formula to use, don't use a formula. Break out your CE312 notes and break out a real moment and a virtual moment, integrate from 0 to L. Y'all remember that? You can do that too, okay? Break out RISA if you need, whatever you need to do. So what I don't want you to do is when it comes to your structural analysis, in other words, computing your moments and you're computing your deflections, I don't want you to be married to a particular formula. I'm happy for you to use them as long as you're using them appropriately. Sound good? Okay. Now, what did we get for a deflection? That's 0.245 inches. Now, what I'm going to go ahead and put up here with this formula, though, this is something that probably is going to be consistent. Don't forget we have a 1728 because remember that's our unit conversion to get our deflections into a proper unit system, right? Okay. Everybody with me? Okay, now let's take a look at the next case, which is dead loads plus the live loads, okay? Now, what's going to change? Look right here. Is WA going to be 1.0? I'm asking you. What's it going to be? 1.7. So this is 1.7 kips per foot. And so what is WL squared over 8? 85. So what's IE? You starting to see why I set it up this way? Otherwise, you're going to have to sit here and write the formulas all over again and so on and so forth. Set it up in a table and it makes your life a little easier. Does anybody know how, what IE is? And here's the formula so you all can plug and chug this. $4198.6, we'll say. Would you agree with that? Do I have a second on that? Okay, and so what's our deflection going to be? Remember, this is the deflection due to dead plus live. 0.467. Do I have a second on that? Do I have a second on that? Okay, I do. All right. Nobody said anything. So if this is the dead load deflection and this is the live load deflection, what is, or the dead plus the live, what is the live load deflection going to be? How are we going to determine that? The difference between the two. And what is the difference between the two? Would you agree? Do I have a second on that? Okay. Now, I'm sure some of you still might not see it. You might go, wait a minute, I still don't see why we can't compute the dead or the live load deflection separately. Why can't we do that? Why can't we just compute the live load deflection separately, Dr. Mike? You're not making any sense. Well, let me show you something. Let's see. Actually, let me. Oh, wrong one. Watch this. What I'm going to do is I'm going to set up a little table, okay? What I'm going to do is I'm going to keep increasing the applied load, and I'm going to show you what happens to deflection as you keep increasing the load, okay? So I'm going to need your help with this. So we'll start off at like 0.1, then we'll say 0.2, 0.3, and we'll just keep increasing the amount of load. Now, given a load, how do I determine the moment? It's, what was it, WL squared over 8? What was the L for this beam? 20. So this times 20 times 20 divided by 8. Would that be a fair statement? Okay, and if I drag, see, here's another thing. I'm going to drag this down to like, we'll say 2.5. And the reason why I'm dragging it down to 2.5 is I want to look at this row with 1 and this row with 1.7 to make sure that our math matches what we did before. Sound good? All right. Now the effective moment of inertia, let's make sure I do that right. So that's 27.39 divided by that cubed. And admittedly, these first answers are a little weird because this implies that the moments are really, really tiny, but that'll be fine. So that times the gross moment of inertia, which was 8,000, plus 1 minus that times 4067. And I know the first answers are a little wonky. The reason why the first answers are a little wonky is because these moments are smaller than the cracking moment. So you're going to see what I do here in a second. Just watch. Are we getting the correct answer here and the correct answer here? That's what we got before. Okay. So again, the reason why we're getting wonky answers up here is because what's happening is you're only putting 5-foot kips of moment, and it only takes 27.39 for it to crack. Okay? So a way of fixing that from a plot standpoint or from a calculation standpoint is anything that's bigger than 8,000, just say 8,000. So any of these are going to be ones where the beam doesn't crack because the moments are really tiny. Sound good? But that's not really going to matter here in a second. Okay. Now for deflections, we take 5 times W times, now what was L again? 20 to the 4th divided by 384 divided by 3122 divided by that. Did y'all know you could do that? You just keep dividing? Talking about that later. Now, am I missing something? There we go. Now, let's put this in a numerical format to where this makes sense. Did we get the right answer here? And did we get the right answer here? Now, how much live load is on there? How much was it? 0.7. Well, what happens if we just compute the live load deflection directly? Look how much deflection we get. We get 0.136. But in all actuality, it deflected a lot more than that because more load causes more cracking. See, here's the thing, okay? If you plot this, let's do a plot. And let's plot what happens when we increase the load on the x-axis and the y-axis we put the deflection. We get this. All right? See, the facts are, I know it's kind of, the scale doesn't really lend it credence, but really it's a very nonlinear problem. Okay? Like if I stretch this out a bit, it's kind of difficult to see, but you can see how this is kind of nonlinear. In other words, what's really happening is it's sort of going up like this, so a little bit of an increase of load is actually causing quite a bit of increase in deflection. And it's a lot easier to see if I take this formula and I stretch it up a bit. See how it's a very nonlinear function? So it's not as easy to say, well, I can just compute the deflection directly. What's going to happen is if you just put the live load on there, you're going to greatly underpredict the amount of live load deflection because that dead load has a significant effect on it. Does that make sense? Everybody okay with that? Okay. All right. I just wanted to make sure that makes sense. Any questions about this so far? Okay. All right. So just to be clear, okay, I just want to make sure that everybody's clear on the example. The purpose of the example was to compute the instantaneous live load deflection. What's the answer? That's the answer because we take the dead plus the live minus the dead to get a deflection of 0.222. Everybody good? Now, here's the thing. That's not the end of the story, okay? The facts are concrete properties change over time. Okay, this is going to be an interesting question. How many of you have heard of the phenomenon of creep? Creep, okay? And we're not talking about a Radiohead song. So, the 90s. Creep is, it actually violates fundamental mechanics of deformable bodies. And what do I mean by that? The way the mechanics of deformable bodies works is we say that loads and resulting deflections are always proportional to one another. You have a rubber band, you yank on it, you put some force on it, and it stretches. You let it go, it goes back to the same place. Okay? But mechanics of deformable bodies also states that if I take a rubber band and I put 5 pounds on it, the deflection is whatever the deflection is forever. It doesn't change as a function of time. Creep is a realistic phenomenon where that principle is violated. I have an example where I think you could visualize creep. It's kind of gross, but it's the easiest way to explain it. Imagine if you had a piece of chewing gum, okay? And you're chewing it up, and you take the chewing gum out of your mouth, right? And you put like a paper clip through the chewing gum, and you attach like a small little weight to it. And you sit there and hold it, okay? And let it just sit there for a day or two, okay? It's going to get dry and gross and whatnot. But that weight, I think it's kind of easy to imagine that it's just going to slowly do this whole thing, right? Okay? But that violates the principles of mechanics of deformable bodies because the load didn't change, but the deflection kept increasing, okay? That's creep. When you have a change in deflection under a constant load over time, okay? Now, there's actually an inverse phenomenon called relaxation, where the length stays fixed, but the force dissipates over time. And there's actually a really easy example for that, and that's a guitar string, okay? You have a guitar string, and you have it tuned, right? And then give it a couple weeks, and what do you have to do to that guitar string? Like my sound effects? You have to tune it, right? So what's happening is that guitar string is remaining fixed between that end fretboard and the mechanism at the end. The length is fixed, but the internal force inside that string is dissipating. That's why what happens with guitar strings when you play that, when you need to tune them, what does that mean when you need to tune it? What do you typically need to do over time with a guitar string when you say tune it? You need to tighten it. You don't need to loosen it. You need to tighten it. It's not as if the force increases inside the string. It's because the force decreases inside the string. So you have to apply more force over time because over time, those molecules inside the string, they kind of realign to dissipate some of that force. They're under stress. The molecular bonds are being stretched. So they're sort of figuring out their way of realigning so they don't have to hold all that load. Okay? Does that make sense? So creep and relaxation are sort of independent phenomenons, but I think they complement one another. Relaxation is something that we have to deal with in pre-stressed concrete design quite a bit because you have this really super tensed cable inside of a bridge girder, and over time the forces in that cable are going to dissipate. Well, there are other things that go along with concrete. Changes in humidity and temperature can cause shrinkage effects where the actual concrete itself will undergo a volume change over time. And so all that stuff is going to affect the deflections. Okay? The deflection today is not the same as the deflection 10 years from now, 5 years from now, what have you. Okay? So that's one phenomenon that we have to address. The other phenomenon that we have to address is the issue of sustained loading. Okay? Let me ask you a question. Let's take an office building, okay? So how many of you have ever been in an office building with cubicles and computers and all that? Okay, all right. So let's imagine a typical day at an office building. So it's 8 o'clock in the morning, 9 o'clock in the morning, whatever, office opens, workers come in, they do their thing, they type away, it's like the Dunder Mifflin Paper Company and all this, right? But at the end of the day, at the Dunder Mifflin Paper Company, the office. But at the end of the day, everybody leaves, right? Unless you're Dwight. I should have like an office themed slide on here. You know, it'd be great. But when it's all said and done, the facts are at the end of the day, the people leave. So would you agree with me that the load is not constant throughout the day? Okay? Now, when we've been talking about loads that we apply to structures, we've been saying something like 80 pounds per square foot represents the worst case scenario, right? So in the Dunder Mifflin Paper Company, that's the people, the computers, all of that stuff. But maybe only 30 or 40% of that load is sustained all the time, right? What is in that building all the time? the desks, the computers, you know, the copier machine, but the people come in and out, right? So one of the questions that we will ask is not so much the live load, but how much of that load is sustained over time. Now, the Dunder Mifflin Paper Company is one example. Another example is a library. Okay, let me ask you this. The library loads that we've been using are something like 150 pounds per square foot. How much of the, if 30% of the load is sustained at the Dunder Mifflin Paper Company, how much of the load, let's say in a library, is sustained? Where do we get the load? And pretty much all that load, right? I'd almost say that 100% of that, from an engineer's perspective, I'd say that if we were designing a library, we need to assume that 100% of that load is sustained because the books aren't going anywhere. Make sense? Now, if you want me to ask you, like, if there's a neat little formula or a plug-and-chug equation to tell you how much load is sustained over the life, I wish I could give you an answer. I can't. That just boils down to engineering judgment. If you're unsure, contact your client or whatnot. But the facts are you as the engineer need to make a judgment that says, here's my structure, it's an office building, the load is 80 pounds per square foot, how much of that load is sustained over its life, and how long does sustained mean? So for instance, like at Marshall, every year it's typical that they'll resurface the floors. So, when they resurface the floors, let's say in an office, everything comes out of the office, So maybe that sustaining period is only a year, that we're designing an office building and 20% of that load is sustained for a period of 1 year. Make sense? It just depends. If you don't know, assume a worst case scenario and you'll see what that means here in a second. Okay, so first off, how do we compute long-term deflections in general? Okay. Well, the way that a long-term deflection works is we take an instantaneous deflection and we adjust it. And we adjust it by what you see right here, okay? What you see right here. Okay, now, this is a function of two quantities. It's a function of this time-dependent factor, which we're going to talk about here in a second, and it's a function of rho prime. Ooh, rho prime. Let's talk about rho prime. What is rho? Anybody remember what rho values are? What's that? Well, no, that's fluids land. No, say it again. It's the reinforcement ratio, right? Remember we would have like a rho design or rho required, right? But what does it mean if you throw a prime on it? It's the compression steel, right? Do you remember when we first started talking about doubly reinforced beams? And I said, why the heck would you even care about the steel up top? And one of the reasons I said, you get a benefit on long-term deflections. And I said, oh, you'll figure that out later. It's later, right? Think about what's going to happen here. What happens if rho increases? Let's look at this equation here. What happens if your rho prime gets bigger and bigger? What happens to this quantity? Like this is algebra. If rho prime gets bigger, what happens to this fraction? It gets smaller. This quantity right here tells you if you've got an immediate deflection, how much do you bump it up to get a long-term deflection. So the more compression steel you put into the beam, you actually get a benefit on long-term deflections. The long-term deflections go down. And that just comes from tests that show that putting steel up top, you actually get a benefit out of long-term deflection performance. So you calculate your rho prime, and then you need a time-dependent factor. Where do you get that time-dependent factor? You get it from this chart. Okay. Now, it's my one sort of gripe with ACI. I wish they had an equation for this chart. They don't. It's just right out of the spec. And so you kind of have to interpolate it a bit. So the way this chart works is it says this is your long-term deflection, your time-dependent factor as a function of time. So first off, as those deflections, or as that time period, as it goes up, those deflections are going to increase. So on the x-axis, we have the duration of the load in months. And on the y-axis, we have our time-dependent factor. So any sustained load that's like 3 months or less, you could probably just take your time-dependent factor to be 1. You could go down a bit. But any load that's sustained longer than 3 months, you're going to bump those deflections up a bit. Okay? Now you notice the graph sort of plateaus. It's kind of asymptotic. What's the absolute maximum value? 2. Okay? So I just want you to keep that in mind, that your time-dependent factor for quote-unquote infinity is 2. And that's going to make sense here in a second. Now I've got here some values that are showing, well, if it's at 12 months, that's about 1.4. If it's at 6 months, it's about 1.2. If you have a time period in between, you're just going to have to interpret the graph. On homework number 7, problem number 2, you do have to actually do that. And I put a note on the homework that says you could get plus or minus, like you might say 1.8 and you might say 1.85. That's fine. If you say 6, that's a problem. So, okay. So here, yes.
On that, I think you talked about with like the resurfacing or stuff like that. Take that as 1 year.
Sorry, ask that again.
Like how you said they take everything out of the resurface.
Mm-hmm.
Like once a year, stuff like that.
Yeah.
Even though they put everything back afterwards, you still only use 12 months.
I probably would, because usually what happens is they're completely unloading it and then loading it back. That's probably what I would use. You might go a little bit higher than that, or if you really just wanted to be conservative and say, let's just say forever, that's fine too. But even if the time period is forever, I would argue the load isn't 100% forever, for an office building. For a library where the loads are really, really high, yeah, you kind of need to do that. I mean, depending upon the building, like for instance, if you're doing some resurfacing work, like I know this happens in like stadiums or large-scale sports facilities and whatnot, that it takes a while to resurface stuff, so they'll completely evacuate everything, and it might take a while. So it depends. So there are instances where you would assume it's all sustained, none. It just depends. So it's a little bit of judgment. So everybody good? So really, in a deflection problem, what you're going to have to compute are really 5 deflections. You're going to have to compute a dead load deflection, a dead plus the live, and then from those 2, we just take the difference, right? But then what you're going to have to compute is a third one, a dead plus sustained live load. Then from that, compute a sustained live load deflection. So when it's all said and done, you really only care about 3. You care about the dead load, the live load, and the sustained live load, because to get the total deflection, you're going to do this. So the way it works, you're going to take your instantaneous live load deflection. What you do is you add your dead load deflection, but then you adjust it by a time-dependent factor or a multiplier, assuming an infinite duration. Why are we assuming an infinite duration for dead loads? They never go anywhere. Exactly right. So our time period should be infinite. And if our time period is infinite, what's our time-dependent factor? 2, right? So this quantity right here, see here we have to look the value up, but for dead loads, we always use 2. Because dead loads are always there. They never go anywhere. Does that make sense? Everybody okay with that? And then for the sustained live load, it depends on how much is sustained and what's the time period. So what we're going to do on our next example, and I'm going to probably call it here in a little bit because I don't want to start combining a bunch of stuff all during lecture, especially when most of you have a celebration coming up in a bit. But what I'm going to say is this. What we're going to do for our next example is we're going to take that same beam and we're going to say, let's assume that 30% of the load is sustained, and let's say that 30% of the load is sustained for a period of 3 years. And then based on that amount of sustained load and that period of time, we're going to compute the deflections. Now we're going to take it one step further on that problem, and we're actually going to compare those deflections against what's allowable. Okay? What do I mean by what's allowable? We're going to do that on Friday. It's not like it's that much material, but I don't want to rush it. There's a lot of equations here. There's a lot of stuff to unpack, and I really don't want to be the guy who's shoving stuff down your throat when we got plenty of time, and it's like y'all are celebrating here in a little bit. So, That's all I got, everybody. We'll see you in 20 minutes. You get an extra 10 minutes to, I don't know, pray or cry or